Ken.
Hello.
Okay. Okay. How was the homework? How did the homework go?
The homework was good. Yeah.
So I posted homework 8 and I made it due. Yeah. Yeah, I think after 30th we have noticed that the first week of May is the exams. So we have about, in April, we have about 4 weeks. So out of that 2 weeks, I'll try to do special relativity, and 2 weeks I'll do Kepler problem. That's where I think preferably it would be nice if we can do Kepler problem for more than about maybe 3 weeks or 4 weeks. 3 weeks maybe, but we will cut short on that a little bit. And again, relativity also, it's nice to go stretch it, but we'll have limited time there. So, so 2 weeks of relativity, 2 weeks of Kepler problem, and stationary action principle. We'll try to finish in a week. I think that's what we might be able to do. There's midterm 2. April 6th. Tuesday. Any questions in general?
No questions. Thank you.
Okay, we want to do stationary action principle again here, but this time with variations at the boundary switched on. And we will see that they have information content in the sense that we can learn a lot about conserved quantities, and that is, we will show that there is a connection between conserved quantities and the symmetry of the system. Symmetry is obeyed by the system, and in this case, by system, we will mean the action that we will write for the system. and that's broadly called the Noether's theorem, and we will talk about that. So, yeah, already done stationary action principle, but in a limited form. What we did earlier is, let me recapitulate a little bit. So we define an action. So this is, so maybe I should define this properly. So there's an action defined. And action is a functional of the path of the particle. So in general, it's a three-dimensional space. And if we are talking about the motion of a particle, it's described by the position of the particle. It's a function of time, but what exactly is that path is what we are looking for. So this is an action of all possible paths, and it can also depend on time. In what sense can it depend on time? So it depends on the endpoints, right? So we say the particle goes from T1 to T2. So I'll describe that clearly when I write the integral form. This is more explicitly, it goes from T1 to T2, an integral T1 to T2, which is integrated upon time, and Lagrangian shows up here. And this is x as a function of time. It also depends on the derivative of x, which is the velocity. That's a velocity as a function of time. And it could explicitly depend on time. That's what is called action, and that's what we have been doing. And here there is a notation that velocity here is, so velocity is defined to be the derivative of x with respect to time. All right, that's what that means. L here, so this is the action. Here L is called Lagrangian. And for a system, once we have a system, we have shown that this can be written as kinetic energy minus the potential energy. It is not the total energy that shows up. And if we were not to make a variation in time, so what we said is if, so this is a if, so let's say with no variation at the boundaries. The boundary means this is T1 and T2. We have shown that this is equal to this comes out to be minus time derivative, partial derivative of the Lagrangian with respect to velocity. Let's say this is time, and this is minus, I suppose, right? Minus height here. No, plus. If we don't make any variation of the boundaries, that's what comes above. And then we said stationary action principle is when you set this to 0. So stationary action principle. Suppose you say that the action that we define is, we give it a fundamental, or we say that is more fundamental and say that that doesn't change with respect to all possible paths. We require this to be equal to 0, which immediately implies that derivative, so that's your Euler-Lagrange equation. That's what we have done. One thing we want to do here today is that we want to release this piece where we don't, here we have not made any changes at the boundaries T1 and T2, but now we will make those changes. But before that, let me quickly define what is called the Lagrangian. We have the we want to define the Hamilton, so Hamiltonian, and we already have the Lagrangian, and Lagrangian depends on the position and velocity, which is actually derivative of position. So it is the position that is important. So let me point that out when we go to the other side of the book. So the point is that the Lagrangian depends on the position x. Let me, for now, suppress the vectorial dependence there. That's just for simplicity here. This is time dependent, and this is your velocity, which I say is. Let me write that as x dot. Maybe, yeah. Let me write that as x dot. Oh, velocity, right? V. So we have velocity v, and that's time t. That's the three quantities it depends on. Let me explicitly say that by saying L is equal to that. What that means is that if I were to take a total derivative of the Lagrangian, this is the partial derivative idea in mathematics, is that if I'm taking the total derivative, I can have an implicit dependence in x, implicit dependence in v, and of course there is explicit dependence in the time in the Lagrangian. So I will say that I could have an implicit dependence in x, which is captured in this form. So that's a chain rule if you want. First take the derivative with x and then the derivative of x with t. This could depend on velocity v, and this will be dv by dt. Notice this is velocity, right? Dx by dt is velocity. That's acceleration. And plus, of course, we can have dependence in the Lagrangian explicit. So that's a definition there. Now let's define a new quantity. This is how Hamiltonian is defined. Remember that we talk about this quantity here, right? V here. This we will define to be your momentum. That's what is called the canonical momentum. We have already used that. So canonical momentum is defined to be P. Again, it can be a vector. So this is partial derivative of L with respect to V. So what's a Hamiltonian? So you say H is defined as, I'll multiply V with P and then subtract out the Lagrangian. That seems like a random subtraction, but there is a purpose here. This is broadly called the Legendre transformation. Yeah, that should be quiz, right? So quiz. Read about Legendre transformation. And what's the connection it has with whatever we are doing here. So now let's see what are the quantities H depends on. So very naively, one would say that L depends on X, V, and T. And now we have introduced a new quantity P. So in general, H should depend on X, V, P, and T. Right? So let me put that as a question mark. Does it depend on all these quantities or not? Right? Maybe the dependence in one of them is not there, and we want to figure that out. And we are going to show now that actually it does not depend on velocity at all. The way this is constructed, that's the idea of Legendre transformation, that if you construct a function like this, it will not depend on this v here. It will be automatically cancelled out. So, so how do we show this? So let's start with this and talk about what are the quantities it depends on. So again, let's take a total derivative of h with respect to t like this. Maybe I should say this is a way of seeing the dependence in the Lagrangian, right? You take a derivative with time. This tells you what is the kind of dependence it has with x. This tells you what are the dependence it has with v. And this tells you what are the dependence it has in t. So similarly, if I were to write an expression for the total derivative of the Hamiltonian in terms of all possibilities, then whatever shows up on the right should tell me what is its dependence. So this is equal to, let me explicitly do this. This is equal to dp by dt. I can hit on p, v, or on L. So this is dp by dt times v plus p times dv by dt and minus of dl by dt. That's your explicitly, just mechanically, if I do this, that's what I get. But now I substitute the total derivative of the Lagrangian in here. So that's equal to dp by dt times v. Let me see. So yeah, let me just write this as v plus p times dv by dt and minus of all that other expression dl by dx times dx by dt minus of, remember that this can be written as p, so I say that's p dv by dt and this is minus l dt. And that's the point here. And this happens for any kind of Legendre transformation, that this cancels out. It tells me that there is no term with velocity dependence here. Like whatever is there in front of this velocity dependence should be interpreted as a dependence of the Hamiltonian. So let me write this again in here. If I were to write this as, clarify this. So this is equal to, let me write this in the front. So this is minus, just changing the order of writing, x by dt. Let this be plus v times dp by dt on our total derivative. And minus L t. What does this mean? If I had a total time derivative of h, and if I were to presume that I don't know what it depends on, so I say it could depend on all three, right? But we are going to show that it doesn't depend on this v. In general, it could depend on all. So if it is like that, I would say this is a partial derivative of h with respect to x times dx by dt plus partial derivative of h with respect to v times dv by dt plus partial derivative of h with respect to p times dp by dt plus h by dt. That's what in general should happen. But when we compare these two equations here, what we learn is that whatever we say is the Hamiltonian, that has a feature that the position dependence in the Hamiltonian is exactly the negative of the position dependence in the Lagrangian. And by negative, I mean, I think I said it wrong. The position dependence of the Hamiltonian and Lagrangian is such that if I were to take a derivative with respect to x, one derivative comes out to be exactly negative of the other. So, so that's a symmetry in that. What about the velocity dependence? There is no velocity dependence here because there is no dv by dt term here. So we say that the h by dv is equal to 0. Whenever a function is, the partial derivative of a function is with respect to velocity is 0, that means it has no dependence in that quantity, and that's 0. And that's important because whenever we write the Hamiltonian, it is necessary that we don't write it as a function of velocity. We should always write it as a function of momentum. For example, kinetic energy is half mv squared in the simple free particle. Kinetic energy is half mv squared, but that's also equal to p squared over 2mv, where p is equal to mv. But if we are writing this as a, whenever we write the Hamiltonian, it is necessary, or at least conceptually, we should always write it in this form. And whenever we write the Lagrangian, we should be writing it as half mv squared. And you will see this being written in that form. It's not very strictly obeyed, but especially when you're doing electromagnetism, where this momentum has this feature going up very clearly, there it should be strictly obeyed. But in the free particle, it's actually innocent. It doesn't matter so much. So that's the Hamilton not depending on the velocity. What about the position dependence? Here, if we compare the coefficients of the total derivative with momentum, and we say that, oh, velocity v actually is equal to the partial derivative of h with respect to the moment. So whatever we write as a Hamiltonian, the dependence of p actually decides what velocity is. So that's a sort of a symmetry between the Lagrangian and the Hamiltonian. Lagrangian decides what is the momentum, and the Hamiltonian decides what's the velocity. Partial derivative of the Lagrangian with respect to velocity gives you what is momentum, and similarly, partial derivative of the Hamiltonian with respect to the momentum gives you the velocity. That's the definition if you want the canonical velocity and the canonical momentum. Finally, the time dependence in the Hamiltonian and Lagrangian are decided by by the following. So that's a quantity or some relations between the Hamiltonian and the Lagrangian. Let's do some example. Let's say, let's do a couple of simple examples maybe. So, any question at this stage, Ken?
Yeah, real quick. You say that the dependence on the Hamiltonian with respect to v is 0.
Yes.
I'm just curious where that came from. Like,
what does that mean?
yeah, like, is that pretty obvious looking at this, or is that from the definition?
Oh, no, it's not a definition. So, okay, usually that's what I was trying to highlight. Maybe I didn't convey that clearly. Notice, so again here, yeah, when I define the Hamiltonian this way, it seems like L depends on X and V. I've introduced the quantity called P here. Then Hamiltonian should depend on X, V, P, and T, right? That's what I put a question mark here. Does it depend on velocity, right? So it seems like it should depend on 4 quantities, correct?
Yeah.
The way I find it. Agreed as of now?
Yes.
So now I'm investigating that. Does it really depend on the velocity? And I'm going to show that it does not. Okay.
Mm-hmm.
That's the idea of partial derivative. Notice if it depends on all these four quantities, and remember all these quantities have implicit time dependency.
Right.
There's an implicit time dependency there. So if I take the total derivative of the Hamiltonian with time, I should get this, right? I can get here T or V or L. V, L. That's the three terms.
I see.
Clear? Right?
Yes.
But the partial or the total derivative of the Lagrangian with time, I have already found out that's three quantities. That depends on only x and v. So that's x dependence, v dependence, and the time dependence. Right?
Yes.
And now that's the important point here. Notice this was actually, when I wrote the Lagrangian, this was actually dl by dv and dv by dt, where P was dl by dv. Is that clear?
Yes.
And due to this construction PV minus L, what happens is that these two cancel out.
I see.
Okay? Now, what's the
Yes.
implication of that? Okay, so that cancels out. So what? Right? So that cancels out, and I have this. Right? Okay?
Mm-hmm.
But now let me go. So that is doing explicitly. But now let me go back here and say, what if I were to do the total Hamiltonian dependence, not assuming that this is a functional of this form, just pretending that this is a total x, v, p, t. Then I would say there is a derivative with x, derivative with v, derivative with p, and derivative with time, right? I should get four terms.
Yes.
But there are only three terms here. Right?
I see.
So if I were to compare these two, it seems like this is actually zero, right? This quantity here is zero by comparing these two.
I see.
Right?
So it's by comparison. I see.
Yeah. It's basically this construction actually kills the velocity dependence.
I see. Okay. Okay.
The Hamiltonian is built like by construction, it does not have any velocity dependence. It is not a definition, it is by construction, like the way you define it. So that's why one should think about Legendre transform. You can do this in general. It is not necessary that you do it in Hamiltonian and Lagrangian. Like in thermodynamics, this is done left and right. Like we keep different free energy, Helmholtz energy, lots of energies we define, right? And all that is because you want to play this game. Like first you want to write it in terms of velocity and there it is volume and pressure. Sometimes you want to write it in terms of volume and temperature. Sometimes you want to write it in terms of pressure and temperature. Which quantity do you want to work with? That's the idea, right?
Thank you. Thank you. Yes.
Here, if you want to work with position and velocity, Lagrangian is the right quantity. If you want to work with position and momentum, then Hamiltonian is the right quantity.
Mm.
Right? So that's by construction. And that plays a very important role in quantum mechanics because quantum mechanics, position and momentum have a fundamental role there. In the sense that, or I shouldn't say fundamental role, they have a central role. Because Heisenberg uncertainty principle is given in terms of position and momentum, not between position and velocity.
Mm.
For free particle, you can say, okay, how does it matter? Position and momentum. Momentum and velocity are just related by mass. But if you bring in a magnetic field, that's not the case anymore.
Mm.
Right? Velocity is completely different quantity and momentum is completely different quantity. Position commutes in a certain way with momentum, and velocity don't even commute. Like velocity, comma velocity is not even commuting there. So it has a non-trivial feature there. And there it becomes very important what what we are talking about, and Hamiltonian becomes the central quantity for quantum mechanics. In fact, to my knowledge, we don't know how to work with quantum mechanics other than the Hamiltonian. It's always a Hamiltonian.
I see. Wow. Okay. This is where it
Like,
comes from. Yeah.
yeah, that's that's because we don't know how to work with anything else, and because uncertainty is written in terms of x and p. For example, what I mean there is that, for example, let's say we write, we write your Schrodinger equation, right? How do we typically we work in quantum mechanics is we will write the Schrodinger equation, but the Schrodinger equation is always written as kinetic energy plus potential energy is equal to energy, and then you replace momentum with derivatives and so on, right? So that's where you begin at the very undergraduate level quantum mechanics. If you do a little bit of advanced quantum mechanics, you will see that you will start with the Hamiltonian and write down the Hamiltonian equations of motion. Right?
Mm-hmm.
But we never write the force equation. Like, we don't know any other way of doing it, put it like that. It would be nice if we can do quantum mechanics in various other ways, and that will get more powerful, but we don't know how to do it. That's a simple way to say it, I think. To my knowledge, you cannot do it any other way, standard, simple, physical process. Okay, so that this all these quantities play an important role there.
Okay.
Did I give a example? You
Yes.
okay?
No. That helped out a lot. Thank you so much. That explains so much. Thank you.
And this is the quantity that says that. Okay. So, yeah. So let me do a simple example instead of a. Yeah, I'm wondering. Yeah, let me not go into too many details. So I can do the magnetic field example, but that will clearly easily take up about 20 minutes or so. And what do you say? You want me to do the magnetic field example, illustrating this very clearly, or should I do a simple example?
I think the magnetic field example would be good if we had enough time.
Let's do it. Yeah, great. Let's do that. Okay. So yeah. Uh, so let's see. Yeah. If we have a charge. First, let me do a simple example. Okay, so straightforward example. This is a mass in uniform gravity. Okay? So just a warm up before we do that. Do the magnetic field example, and we know what that is, right? So kinetic energy is half mv square. Let me say k is equal to half mv square, and let me just straight away write the Lagrangians, right? So Lagrangian L is equal to half mv square, where v is dz by dt. So we're talking about gravity downward, z is in the upward direction, and a particle is falling, right, in that manner. So it is mgz, that's your gravitational potential energy. So that's minus mgz, where velocity V is dz by dt. Everything is happening in a straight line. What other quantities L depends on? So L depends on z as a function of time, and z dot, which is velocity as a function of time, and time t itself. What's our momentum? So this is momentum. P is equal to partial derivative of L with respect to velocity V. That's equal to mass times velocity. Right? Straightforward, simple case here. Of course, we have time. Our Euler-Lagrange equation will be time derivative of dL by dV is equal to dL by d. Actually, let me write that explicitly here. So partial derivative of L with respect to z is equal to minus mg, and partial derivative of v is mv, and that is partial derivative of L with respect to time, that's equal to 0. No time dependence in there. And time derivative of this equal to minus mg is your equation of motion. What about the Hamiltonian? Hamiltonian is now p times v, so that's or v times p minus L. So that's equal to v times p is mv. So let me write that as p minus L, which is half mv squared plus mgz. Now it is convenient, or often you will see, why not write this as let's say I replace p with mv, so that's mv squared, so that's half mv squared plus mgz. That's okay, right? That's as far as numerical quantity goes, that's okay. But notice that we already said that the Hamiltonian should not be written in terms of velocity, so that's kind of it's misleading in a sense. It's as a numerically correct. That's what is software is. That as a value, if you were to evaluate this at a certain time, that will surely come out to be the Hamiltonian, but it is not correct in the functional sense. It should not depend on the velocity. So what it should be is that we should replace the velocity v. So you would say this is p squared over 2m. So this is p squared of this will be p squared over m. This will be p squared over 2m. So that's p squared over 2m plus mgz. And in this manner, this is z, comma p, and comma t. That's your Hamiltonian. What are the quantities it depends on? The h by d z. This is, of course, mg. Right? And now remember that partial derivative of x is exactly negative of that. And what about the partial derivative of h with respect to p? That's equal to p over m, which we define is which by definition is the velocity, and dh by dt is equal to 0. In general, I haven't explicitly derived it, but it's a straightforward quantity that is also what is called Hamilton equations of motion. Hamilton equations of motion. In general, like always, right, which we will verify with this, is that Hamiltonian depends on position and momentum. So this is if you want the velocity, and this is your force. How does the position change with time? How does the momentum change with time? Hamiltonian depends depends only on x and p. And always this is equal to partial derivative of the Hamiltonian with respect to the momentum. And this is equal to the partial derivative of the Hamiltonian with respect to the position, but with a negative sign. Notice in our case, what we have is dx by dt, that's your velocity. So what we are saying is that velocity is equal to partial derivative of h with respect to p, so that's p over mv, p over m. Of course, we have p is equal to mv. So that's one equation of motion, if you want the definition of velocity. And the second one is the force equation, right? The derivative of momentum with time dp by dt is equal to partial derivative of h with respect to z in our case, which is minus mg, which is of course the equation of motion if we were to do Newtonian physics, right? So of course, finally we do get everything to be consistent, but that's the way you would write. So that's a very simple or trivial, in a way trivial. All these things do not make too much significance there, because a small change in the mass shows up here or there. That's all. That's the difference. Any questions there before I do the magnetic field case?
No questions. Thank you.
So now let's do the magnetic field problem. So let's do the first. Let's write down the Lagrange, right? So charge is an example is charge in a magnetic field. Example is charge in a magnetic field. Remember Newtonian way of doing it. So Newtonian equation of motion for a charge in a magnetic field will be d by dt of mass times velocity. This is the actual velocity of the charge, right? That's equal to qvb, right? qv crossed with b. Correct? Now let's, since I want to recognize what is the connection between V and B, first of all, let me just do it the straightforward way, or should I? Yeah, so let's remember we also have B is equal to del cross A. Is that a familiar idea? Vector potential?
Yes. Yeah.
So we have del crossed with A, so this is Q times B crossed with the gradient operator acting on A, where A could be a function of X, but not on velocity. Right? Vector potential does not depend on velocity. That's this. And V is not a position dependent quantity, that's the velocity of the particle, that in general it will not depend on the position, right? That wherever the charge is, that is all that depends on. Let's expand this out. So we have Q times gradient of V started with A. Here I have assumed that V actually does not depend on the coordinates. It is only a position of the charge dependent quantity. Minus of Q times V started with the gradient operator of the vector potential A. move this onto the left, and yeah, maybe I should clarify this a little bit. Yeah, for the time being, temporarily, actually, let me actually introduce the electric field. That's good to see where it is coming in from. So it is Q, that is an electric field also, let's say. Because I'm going to add and subtract something to this, and instead of saying that it's an assumption, let me say it is electric field is in there. And electric field is Q times negative gradient of the scalar potential negative partial derivative of A time. Is that a familiar idea? Electric field is equal to this?
Yes. Yeah.
So I have one more piece then. So I have negative Q times gradient of potential, and I have negative Q partial derivative of A with respect to time. Okay, all this to see the connection between velocity and momentum at the Newtonian level. So we have this says that partial derivative of dt times mv. Let me bring few of these quantities to the left. I have plus q, that's plus partial derivative of time, and I also have q times v times gradient, so it is plus v dotted with the gradient. Those two quantities, let me bring it to the left, and this is q times a. So what I've done is this I have taken to the left, and this term also I have taken to the whatever is on the right remaining then is a gradient of some quantity, and that's a negative gradient of some quantity, and this is equal to q times phi, and this is minus q of v dotted a. As of now, it's just manipulation or algebraic manipulations, but plays an important role at this point. This is nothing but a total derivative. If some quantity depends only on the position, then this is simply total derivative. So this is d by dt. Is that clear, or should I clarify?
No, I think that makes sense. Yeah.
Okay. So what we have is the total derivative of some quantity here, so that's mass times velocity, plus q times the vector potential, which is only a position dependent quantity, and it can depend on time actually. Is equal to the negative gradient of q. So this is your electric potential, right? Q times v, charge times the potential to the point charge, for example. And this is minus the magnetic energy, if you want. Conserved quantities. At this stage, you recognize the Lagrangian. Oh, okay, what does this mean? Now I compare this with my Euler-Lagrange equation. Euler-Lagrange equation says this has to be velocity. Right? And this is basically gradient, right? So that's gradient of Lagrangian. That's my Euler-Lagrange equation, and that immediately tells me, oh, what does this mean? Oh, maybe I should actually, there's an easier route than this. Let us actually go back and remember there was one more equation I wrote that for Hamiltonian, I have the time derivative of the momentum is equal to the negative gradient of the Hamiltonian. Is that just now I wrote a few lines back when I was talking about the Hamiltonian, we did that. So this one here. Okay. And which is much more common thing than I should point out. This is force, right? Force is the negative gradient of Hamiltonian, typically is the energy, right? Force is equal to negative gradient of the energy. That's the statement of one of the Hamiltonian equations. And if I were to compare this and this equation, it seems to suggest that, oh, I can read out what is momentum, I can read out what is Hamiltonian, right? So at that stage there, I learned that from Newtonian physics, I learned that momentum is equal to mv plus q times a, where a is a function of position. And I also learned that the Hamiltonian, which is a function of position and momentum, is equal to q times the scalar potential minus q times v dotted with a. Let's instead of going from the Lagrangian to the Hamiltonian, that is now I'm going to go from the Hamiltonian to the Lagrangian, and at this stage we can immediately ask, oh, is this okay or not? Because I'm going to write the Hamiltonian, right? Because what I said is that Hamiltonian has to be written in terms of your momentum, correct? So you cannot write this then. Agreed? So it has to be written in terms of velocity. Right? So you would say, oh, okay, so I'm stuck here. So this, you would say this is q times phi. Position dependence is okay, remember, right? A is dependent on x, that's okay. So there is position dependence minus q. I have to replace the velocity in terms of the momentum and position. So that's, I would say this is p minus q times a, which is a function of x, divided by m dotted with a. Oops. Right, so that's equal. Yeah, I messed up. Sorry. What did I mess up? Yeah, how I messed up here is that I took this to be the complete Hamiltonian. That's not the complete Hamiltonian, right? Because this is only the gradient of the Hamiltonian. I could have always killed a position or the velocity dependence in there, because that will be constant. Correct? So actually I should go back and work on that. Did I explain that or do you see the mistake? I think I should go back.
You're saying that the gradient of the V is 0?
Yeah, but what I'm trying to say is that from this statement here, comparing these two, correct? I immediately wrote my Hamiltonian to be this.
Mm-hmm.
But I've always had a velocity dependent term, for example, half mv squared. And it would have always killed it because gradient with respect to that is 0. So let's
Right.
not use this, let's go back in there. So I want to say that this is actually wrong. The Hamiltonian that I have written is wrong. When I was reading it, this doesn't imply that. This alone does not imply that. Plus a function of v, plus some constant, which can be a velocity dependent term or actually a momentum dependent term. Okay? Is that clear? What I'm suggesting? No.
Yes.
Yeah, so since I'm missing that, let me go back since Lagrangian here is much more explicit. Let me go back there. I was thinking it would be easier just to go through the Hamiltonian, but let's go through the Lagrangian. It won't come. Okay. So this equation is satisfied. If I compare these two, immediately I can see that L would be equal. So this tells me that is this. So I should have half E plus Q times V dotted with A. That's plus Q. So then minus Q times phi. That's your Lagrangian. Let's check whether this is correct or not. If I were to take the partial derivative with velocity, I should get this. If I take the partial derivative with velocity, I get mv, that's this term, and I get q times a, that's this term. That works out well. What about the gradient with respect to Lagrangian? There is no position dependence here. That is a position dependence in the a, which is with a positive quantity. That's a positive term, and here there is a gradient inside this, that's the negative. So that's your Lagrangian, which is a function of x and v. And let me explicitly show where the x and v is. X and that's your velocity, and this is equal to L, position, velocity, and time. Like this could also be time dependent, right? Is that clear now?
Yes.
Okay, so that's our Lagrangian, and momentum P would be derivative with respect to velocity, which is mv plus q times a. Notice it is not mass times velocity, very different, right? There's a whole function that you're adding onto that. The momentum is not velocity, m times v. So what is Hamiltonian? So Hamiltonian is equal to p times v, so or v times p, v dotted with p, minus the Lagrangian. Okay. Yeah. Let me go to the other side of the board so that. So what I have here is so charge in a magnetic field is described by position, velocity by the Lagrangian, which is position, velocity, time, and then that's work of v square and plus q times v dotted with a, which can depend on x and t, minus q, that's a scalar potential, which can depend on x and t. Momentum is mv plus q times a. That's a explicit dependence. Then comes the Hamiltonian. Hamiltonian is defined as v dotted with p, but Hamiltonian has to be with position and momentum, not no velocity should show up, or by construction it is never there. But let's see how it goes through. So v can solve replace it. So this is v is p minus q times a over m dotted with p. It seems like it's taking an odd construction here, but let's go back to our Lagrangian L, right? So that's half m squared minus of q b dotted with a and minus q times phi. So it's just mixed up in the sense that is somewhere there is velocity, somewhere there is momentum, but I have to kill all the velocity dependence. So let me collect them. So this is p square over 2m. So there is p square over m actually, minus q over m times a dotted with p. I could have done it if I had collected it at this stage itself, but let me do this. Minus of, there are two mv's there. mv is p minus qa minus qa. What? That's this, and I have minus v. So v is again p minus qa. So it is q times p. So q times a. Q times a and p minus qa. Yeah. P minus qa over m times qa minus q phi. So now everything is in terms of p, but there is a lot of simplification, of course, and it will significantly simplify actually. So let's collect these terms. Okay, there's a p square over 2m here. Let me expand it all out. P square over m minus p over m dotted with q times a. Then there is a p square over 2m minus p square over 2m minus again of q a square over 2m, and that is plus 2 cancels out, that is 1 over m and p dotted with qa. I have finished with the p of that. And finally, I have minus p over m dotted with q times a plus qa squared over m and minus q phi. There should be cancellations here. We collect all of them. This is p square over m, p square over 2m. That's p square over 2m. One term, no, not this. P square over 2m is here. And then I have qa over m, qa over m, so that's plus 2a square over 2. That's these two terms. And then let me collect the cross terms, p and q, so these two cancel out. These two cancel out. And there is another one of them down here, which can be written as 2 times p dotted with q times a over 2m. That's this term. And I've collected most of the term except minus q phi. Which is equal to p minus q times the vector potential, which is x dependent or time dependent, squared over 2m. It's just half mv squared if you want, minus q times phi. So to make it more explicit, this is nothing but symbolically, right? So maybe put a question mark there. This is nothing but half mv squared minus q times phi. The Hamiltonian is a function of x, p, and t is this, with the idea that mass times velocity should be only seen as a symbol for p minus qa. So notice this is very misleading because it seems like there is kinetic energy and there is a scalar potential. Where is the magnetic field? Oh, magnetic field is inside the velocity because there is this A inside here. In fact, Hamiltonian cannot be written in this form, it should be written in this form. But if you understand that MV actually represents that, there is nothing wrong in writing that as far as you don't make mistakes with them. Does that clarify?
Yeah, I think so.
It's a little involved, but if you go through it, you see the essence that velocity and momentum are the Hamiltonian dependence is always in momentum. And this example clearly has it in every sense of the word, especially when you go to quantum mechanics. I think somewhere else, yeah, let's keep this as a quiz, not a very easy quiz, right? In the sense that it takes you to quantum mechanics. What is V commutator between V and V? So that's your velocity and velocity, two operators commuting with itself. You would say, oh, that very naively speaking, it shouldn't be zero, but it's not in quantum mechanics. Remember, angular momentum does not commute with itself, right? So this is not zero. And it has interesting consequences, like whatever physics we see in a magnetic field can be explained, or this is at the heart of that if you want. So this, I haven't reached there, but we will be digressing too far to reach that. Okay. But keep this in mind, maybe that's the best way to put it. Keep this non-triviality in picture, and whenever you're doing quantum mechanics somewhere else, fill this up. Okay. Is that reasonable?
Yeah.
And go through it and ask me again. I mean, you usually come and ask questions, so ask me again and I will clarify. Yeah.
Right. Okay. Yeah, I'll go through it again.
There's a lot of reasons in there.
Yes. Very.
Okay, I think I will stop here. Hopefully. And I was wanting to do that variation thing, but that's okay. We will do it slowly. Any questions, comments? And actually, maybe I can comment here. It is kind of clear why this does not commute, right? V has momentum in it, and it also has position in it.
Right.
And momentum and position do not commute, so this doesn't commute.
Right.
Kind of there, right in front of you. But it has physical consequences.
Okay. All right. Well, thank you very much.
Welcome. Yeah. Bye, Ken. Have a nice day.
Oh yeah. Bye. You have a good one too.